Hello and welcome everyone. So in this video I'm going to talk about cooperation and coordination, largely in the context of game theory, in particular referencing the repeated prisoner's dilemma, but then some other types of games, obviously, with applications of coordination and different types of coordination mechanisms. All right, so here's a picture of my dog being somewhat uncooperative, not wanting to come inside. Again, this is always more useful to me than everyone else to have dog there, because this will show up in the thumbnail if I have it up long enough, which is good, at least on my desktop. All right, so in terms of references for the book, so Axelrod, Dave Schmidt's What Nozick Did for Decision Theory is relevant for framing, and then the coordination game comes from Lansing and Miller, Cooperation Games and Ecological Feedback. The Axelrod book, just clarify, this is interesting, and I would like to actually make this what I would have liked to have made this one of the books for the class, except that we can kind of get into the details here in the context of the lecture, and I guess even though I make everybody go out and buy the book for a framework that some ideas will be able to apply, but I don't know. So I didn't want to do that, but I do recommend it, strongly recommend it. It's a really interesting book, and sort of interesting thinking about applications of game theory, in particular in the context of cooperation. All right, so the motivating question and first sentence from the book, this is the older edition than what I had in Amazon there, but under what conditions will cooperation emerge in a world of egoists without central authority? So think about sort of decentralized situation, much like a sort of market economy. Where will we get cooperation? How can we get cooperation towards societal goals and so on and so forth? All right, so Axelrod uses the prisoner's dilemma as a model within which to study the prospects for cooperation, in particular the repeated prisoner's dilemma. One of the reasons why the prisoner's dilemma is super interesting is because it's a social dilemma. When it's framed as a one-shot game, you're not going to get cooperation. You're going to get individuals behaving in their own interests, following dominant strategies, leading to a miserable equilibrium. It is only when it's repeated that we're able to sustain cooperation as an equilibrium. Actually, in the repeated prisoner's dilemma, you get a whole continuum of equilibria. But anyway, so in the standard prisoner's dilemma game, we've got two players. They've got choices: cooperate or defect. Each chooses it's simultaneously timed. Each chooses without knowing what the other player will do. Actually, in the one-shot, once played prisoner's dilemma game, it doesn't matter if you know what the co-player is going to do, as long as you know that everybody's got a dominant strategy. So regardless of the choice of the rival player, defect always yields a higher payoff than cooperation. Defect is a dominant strategy. So there's a problem. Here's the dilemma. This is what makes it a dilemma. If both defect, both do worse than if they had both cooperated. Right? So if they had cooperated, when you play, so here's the features of a prisoner's dilemma. Everybody's got a dominant strategy, and if you were to both play your non-dominant strategy, the social surplus is higher, right? You do better if you both play your non-dominant strategy than if you use your non-dominant strategy. So here's the game. Let me actually go through those two statements I made a second ago. So You've got two players. Each has a strategy to cooperate or to defect. So row player chooses to cooperate and controls the top row of the matrix by choosing cooperate, or chooses defect, which is the bottom row of the matrix. Column player chooses to cooperate. It's not going to let me highlight. They're choosing the left column, or to defect, they're choosing the right column. And when one person chooses a row and the other person chooses a column, that picks out one of the cells of the matrix. So for instance, if they both cooperate, they both get payoff of 3. If they both defect, they both will get a payoff of 1. If one cooperates and the other defects, whoever cooperates gets 0, and whoever defects gets 5. All right, so we see actually indeed they are doing worse if they both cooperate than if they both they're doing worse if they both defect than if they cooperate. Okay, so we've got that. Also, if you sum up the payoffs, just add 1 plus 1, that's 2. 5 plus 0 is 5. 5 plus 0 is 5. And 3 plus 3 is 6. The highest social surplus is if they both use their non-dominant strategy. 6 is bigger than 5 is bigger than 2. So it's a social dilemma. Anyway, so if they cooperate, they receive R, the reward for mutual cooperation. If one cooperates but the other defects, whoever defects gets T, the temptation to defect. Here that's 5. The cooperator gets S, the sucker's payoff. That's 0. If they are each defecting, they each receive P, the punishment for mutual defection, right? All right. So here's the fundamental features of a prisoner's dilemma game. So firstly, there's no mechanism for enforceable threats or commitments. So there's no way to come up with side payments or to reinforce promises or whatever, right? It's just the payoffs, you choose your strategies, that's the outcome. Also, there's no way to be sure what the other player will do on a given move, right? The only information is the history thus far in the game. So if we're playing this repeatedly, you don't know what the player is going to do next. You know what they've done previously. You've observed that, and maybe it predicts the future. Who knows? There's no way to eliminate the other, or no way to eliminate the other player or run away from the interaction. You're stuck. You've got to play this game. And there's no way to change the other player's payoffs. So how do we get cooperation? Well, what makes it possible for cooperation is the fact that players might meet again. But the future is less valuable than the present. You might discount the future. All right, so we're able to get cooperation in the repeated prisoner's dilemma game because it's repeated, because there's the shadow of the future, but the future is not as valuable as the present. So there's this temptation to well, in this case, we call this a temptation to defect, right? Okay, so the additional characteristics of the prisoner's dilemma game, well, the payoffs don't need to be comparable. They could be very different. So we could have different numbers as long as it preserves the same essential features, which is that they're both doing worse when they both defect than if they were to both play their non-dominant strategy. Payoffs do not need to be symmetric. This is convenient but not essential. They don't need to be measured on an absolute scale. They can be utilities where only order matters. Remember, utility is an ordinal concept. With utility, what matters is order, not the magnitude. All right, so additional characteristics. Well, cooperation need not be considered desirable from the perspective of the outside world. So in the context of collusion or cartels, right? So it doesn't have to be the case that everybody else wants the cooperation to happen. It could be the case that everybody else doesn't want cooperation in the case of collusion and cartels, right? It's just got to be the case that collusion is desirable within the relationship of the two players. There's no need to assume rationality. You could actually select strategies on simple heuristics, habits, instincts, or whatever. The actions don't even need to be conscious choices. No need to assume deliberate choice. The actions could be selected without any regard to a strategy. All right, so giving rise now to exploring cooperation. So now we're going to that Axelrod book. That was, this book right here. So the write-up here, the book is sort of the write-up of, or the book recounts a write-up of this computer tournament. So what ended up happening was Axelrod invited professional game theorists to submit entries for this Prisoner's Dilemma tournament. So basically, people that had an interest, academics that had been working on the Prisoner's Dilemma, the basic idea was to recruit a lot of individuals who had thought carefully about the Prisoner's Dilemma to submit a strategy that was then placed into this computer tournament. So the submitted strategies were paired against each other in a round-robin tournament. So the idea was you'd play one player and then the other player, where the players were strategies that had been submitted by those who had studied or published recently or had some interest in the Prisoner's Dilemma to that point. Each strategy was paired with its own twin and then with random. So random was a program randomly selecting cooperate and defect with 50-50 probability. So the submitted strategies played against all the other strategies, played against itself, and then played against a completely random strategy. Each game consisted of 200 moves and then used the payoff matrix shown in the introduction of the slides, right? So this was the payoff matrix. The entire tournament was run 5 times to get a more stable estimate of the scores for each pair of players. So there's 14 submitted entries from, academics from psychology, econ, poli-sci, math, and sociology. Most of the entrants were recruited from those who had published articles on game theory in general or from the prisoner's dilemma in particular. Right? So people had thought about game theory, thought about the prisoner's dilemma. Interestingly, maybe you've heard of this already, tit for tat was the one that won the tournament, right? It was the simplest of all strategies. What tit for tat did was begins with cooperation, then mirrored what the rival player did on the previous move. So as a result, having observed how tit for tat did in this population, Axelrod's advice from the prisoner's dilemma based on the tournament is, firstly, don't be envious, don't be the first to defect, reciprocate both cooperation and defection, and don't be too clever. Don't be envious, meaning don't try to pay off steal or try to seek a higher payoff than your co-player, right? The only way that you do that in the prisoner's dilemma is to defect, and that's bad because that leads to more defection. So don't be envious, be nice instead. Don't be the first to defect, right? Start off cooperating, reciprocate both cooperation and defection. So cooperate with those who are cooperating, but defect if the other person's defecting, the other strategy is defecting, right? Don't try to be too clever. So some of the Axelrod is in the book, and then in the write-up talking about some of the strategies being pretty complex. You don't want to try to outthink the room. You don't want to try to be too clever. Axelrod's advice for those interested in promoting cooperation based on the tournament. So now what do we learn from this tournament then thinking about cooperation more generally? Well, you want to enlarge the shadow of the future, right? Take advantage of repeated play and reputation. Try to change the payoffs, right? Make sure that individuals do not have private incentives to cooperate. They'll be required to do the socially useful thing anyway, right? Make sure that when individuals don't have private incentives to cooperate, they have to do whatever is socially useful anyway. Teach people to care about each other, teach reciprocity, and then improve recognition abilities to help players remember past interactions in order to sustain cooperation, to reinforce reputation. Teach reciprocity, right? Reciprocating both cooperation and defection. Teach people to care about each other, so on and so forth, right? So these are all sort of really good advice for promoting cooperation. All right, so I'm going to next talk about framing. But anyway, as we take these items for these pieces of advice for sustaining cooperation and thinking about cooperation in the context of a repeated prisoner's dilemma, I think this can be really useful for thinking about cooperation actually in human societies. And hopefully you find this useful as I have. All right, so framing. So this is following actually from the rational choosing lecture, thinking about, I introduced this with Newcomb's problem. So the way players think about the game being played is really important. When trying to model a scenario, we often assume both players have the same expectations about the game form. But there's different ways to partition the possible states of the world, right? And apart from the goals and motivations, people differ in the perception of what's even going on, right? Are we even playing a cooperation game, or is it a payoff stealing game, right? So even apart from the issues associated with like how are we partitioning and how are we thinking about this game, how are we thinking about the states of the world modeled in the game, it's like, are we thinking about this as a game where we're working together or working against each other? That's important. All right, so here's a standard prisoner's dilemma. So you cooperate, you defect, your partner cooperates, your partner defects. And so these are just the payoffs from before. We could replace these with like, this was 3, this was 5, this was 3, this was 0, this was 0, this was 5, this was 1, this was 1. Both had a dominant strategy to defect. Is cooperation rational here? Well, not in the one-shot game. In the repeated game, though, here's the alternative partition. So suppose we think of this game as your partner plays like you, your partner plays unlike you. If they're playing like you, cooperate, cooperate. If they're playing unlike you, right? So if they play like you and you cooperate, you both cooperate. If they're like you and you defect and they're going to defect also, you both get 1. If they're not like you, they're going to do the opposite, and then, that's not good. What's happening is this partition is thinking about the prisoner's game a prisoner's dilemma game is something a lot more like a coordination game. Now, is cooperation rational? So that's interesting, right? In some sense, this partition is a mistake. Thinking about the game like this is a little bit of a mistake. But even so, sometimes we want to think carefully about, like, how are we thinking about this game? How are we thinking about the decision problem? And there's some value in thinking about the role of framing. Okay. The last thing I want to talk about is coordination. So some situations actually are modeled as a coordination game. And so here, a key feature with a coordination game is we've got multiple equilibria, and players are doing better when they match their actions with their co-player, right? When they coordinate. There's little internal direction from the game's structure as to which outcomes the players might gravitate to. That's sort of the hallmark of a coordination game. So here's an example of a coordination game. So we have row player choosing up or down, column player choosing left or right. If row chooses up and column chooses left, row gets 3, column gets 1. If row chooses down, column chooses right, row gets 1, column gets 3. So we have two Nash equilibria. If you solve by best responses, two Nash equilibria are going to be up left and down right. Which do we expect? I don't know. One is better for row player, up left. One is better for column player, down right. But both would rather see their co-player get the high payoff than both get 0, right? Because one is bigger than 0. All right, so in such situations, some external coordination device can help choose between which of the equilibria will be played. So this involves some type of additional information that can make one of the outcomes more focal. So for instance, University of Michigan campus, students trying to arrange a study group might convene at the ugly even without prior agreement. Think about it. If you're gonna join up with a study group and you just said, "Oh, all right, we're gonna study for the exam. We'll meet at 7 o'clock, 8 o'clock, 9 o'clock, or whatever," and that's all you've got. You didn't say where. A natural place to meet would be the library, right? Or I guess go to where the lecture is held, or some other place, maybe go to the mall, where some other place on campus that would be sort of a natural meeting place where you could both rationalize the rest of the group coordinating on meeting, given that you haven't pre-specified where to meet and maybe you forgot to exchange contact information. Anyway, so the library would be an example of a focal point. It'd be kind of a natural place where you might reasonably expect the other people to show up if you haven't predetermined where exactly you're meeting. In other cases, there's other external conventions that assist coordination. So for instance, do you drive on the left or you drive on the right? Well, that decision is solved for you based on the convention of the locality, right? So in some countries, you'll drive on the right side of the road. In other countries, you drive on the left side of the road. And you want to coordinate with what people are doing, right? This is definitely a place where, when in Rome, you want to do as the Romans do, right? If they're driving on the right, you better be driving on the right. If they're driving on the left, you better be driving on the left. And you don't want to fail to coordinate in the driving game or in the walking down the hallway game, whatever is the case. All right, so next I'll consider Lansing and Miller. So this introduces an interesting coordination device from anthropology. All right, so Lansing and Miller are thinking about barley. So rice is grown in paddy fields using this elaborate irrigation scheme. Now, water demands are at the highest at the start of the new planting cycle. You got to saturate the dry fields to be able to make planting successful. Now, also, flooding and draining, this effect has an important effect on pests, right? It's going to kill them and destroy their habitat. It's going to get rid of the pests that can be harmful to the crop. So here's a scenario. If farmers with adjacent fields synchronize their cropping patterns to create flooding across a wide area, the pests are deprived of habitat and there's going to be fewer pests. The problem, if too many farmers do this at the same time, peak water demands coincide, there's not enough water. So that's bad because you're also, not only are you not killing the pests, you're also not having enough water for your planting. All right, so they're going to model the situation with a simple game. We've got two representative farmers. One is upstream from the other. Each has to decide to plant on one of 2 days, A or B. There's enough water for one farmer, not enough for simultaneous planting. So here's the payoffs. Now I'm going to show the table in a second, but we'll have delta is between 0 and 1. This is the crop loss to the downstream farmer due to insufficient water. Right? If the upstream farmer takes the water, there's not enough for the downstream farmer, so the downstream farmer is going to lose. Now, if the farmers don't plant simultaneously, both suffer damage to pests or from pests. So this is rho in 0 to 1, right? Is the damage from the pests. So here's my upstream farmer choosing date A, upstream farmer choosing date B, downstream farmer choosing date A, downstream farmer choosing date B. So they've normalized the payoffs to an undamaged field at 1, right? So there's an undamaged field if we both plant on, or undamaged field, sorry, for my upstream farmer, if we both plant on day A, the downstream farmer suffers a damage due to what? Loss of insufficient water, right? Suppose if we coordinate and the upstream farmer plants on date B, upstream farmer gets a whole field, downstream farmer again loses. Now, if we fail to coordinate, we both suffer a loss due to pests. All right, so this is a nice coordination game. Now, you can work this out. I've got a video on solving for mixed strategy Nash equilibria. You could do this. You could solve and reinforce these equilibria. There's a unique mixed strategy Nash equilibria. So that's this right here. We also get two pure strategy equilibria involving coordination if delta is smaller than rho. If delta is smaller than rho. So coordination actually yields a payoff that's higher than the mixed outcome if rho is bigger than half delta, right? So you can go to the paper, you can work out kind of the theory for this being the case, or you could just take this at face value just for the context of explaining the example here. Anyway, so the logic to what's going on here has important externalities that are at play. So firstly, there is an externality of water damage, delta, imposed by the upstream farmer on the downstream farmer, right? If they plant on the same day, the downstream farmer is harmed by this negative externality exerted by the upstream farmer's decision to plant. Then there's pest damage imposed on both from each other by staggered cropping. If they fail to coordinate, they're both going to exert a negative externality on each other. Now, the upstream farmer doesn't face water scarcity and always has an incentive to minimize pest damage by simultaneous cropping. However, the downstream farmer faces either and chooses the lesser of the two evils, right? The downstream farmer has to deal with both problems. The upstream farmer only has to deal with pests. Anyway, we've got to solve this problem. So what did they do? How did they solve this problem? Well, in parallel to the physical system of terraces and irrigation works, there is an intricate network of shrines and temples. These are dedicated to agricultural deities, to the goddess of the lake, and the temples provide a way to coordinate the cropping patterns. So now the temples and this sort of religious structure that's kind of built alongside and parallel to the waterworks is serving as this coordination device and is kind of keeping people on the same page to the extent that the temples and the workings in the temples are providing a good enough guide. Anyway, this is sort of an interesting situation where you've got this social problem and you've got this external coordination device, in this case the religious function, that is able to help the society overcome this coordination problem. And you can look for kind of similar things around human society. Actually, there's a lot of interesting applications for solving coordination problems, and a lot of stories you can tell about culture, social norms, and so on and so forth that are seeking to either solve problems of coordination or problems of cooperation. So this is something to kind of keep in mind as you look around you, and then certainly throughout the course. So anyway, I'll go ahead and conclude here. Hope you enjoyed the lecture. I'll see you in the next one.